All right, hello everyone. I am going to be doing a mechanics paper with you. So today we are going to be looking at the February-March 2023 paper. It's an hour and 15 minutes, and once again, this is for mechanics. So my goal is to just go through this paper. I'm pretty much going to try and go as quickly as I can and talk through the subject as I go, but I want to try and do it at the pace at which you would need to be doing your mechanics exam. So that's my goal. And then I hope to just share all my thoughts as I'm going. My students have asked me to, I don't know, they just want to see how I would do a paper. So that's the goal for today. I am going to pull up the memo just alongside me, but I don't want to use the memo. I haven't looked at the paper before. I don't want to use the memo in solving these questions, but I will just take a look to make sure that we're getting each question 100% correctly. All right, 100% correct, I should say. All right, so before you go into mechanics exam, just make sure that you've read all the questions correctly. And the next thing that you also want to make sure is that you go in with your calculator on degree mode. So mine was on radians. Make sure it's in degree mode. Before you go into the paper, you always want to be using degrees, not radians. All right, I'm not going to go through the rest of the instructions in this video. Okay, so first of all, we see there is a crate of mass 200 kgs and it's being pulled at a constant speed along a horizontal ground. Okay, every single word here has some sort of meaning to it. Okay, so there's a crate. First of all, we know it's on horizontal ground. So I'm going to draw my horizontal ground. My crate is just a square. Okay, 200 kgs. And then constant speed. So that means there's no acceleration. Acceleration is zero. Whatever's going forwards is also going back. Some of my forces going forwards is the same as for some forces going back. Okay, but let's just keep reading. On a horizontal ground, and then by a rope attached to a winch. Okay, so a winch is the machine that is going to pull this thing. The winch is working at a constant rate. Okay, so this thing is being pulled here by a winch. It doesn't matter what it looks like. The power of the winch is 4.5 kilowatts. In other words, 4,500 watts. So make sure you're always working in watts in your power formulas. Just out of interest, I know that power is work done divided by time, and power is my driving force times my velocity. This specific velocity either needs to be at an instant or if there's a constant velocity. So this is just the theory behind these questions. Okay, there is a constant resistance to the motion, so that's going to be our frictional force of 600 newtons. Okay, find the time that it takes for the crate to move a distance of 15 meters. Okay, so we want to find the time. So each thing that they're asking us, so we want to know what is the time. So our answer is going to be in seconds. Find the time that it takes the crate to move a distance of 15 meters. Okay, so first things first. I know that sum of my forces is going to be equal to 0. So if I just start writing that down, I can use Newton's second law. So my sum of my forces is my mass times acceleration. And in this case, my acceleration is 0. It's not accelerating. So I've got my driving force going forward, and I've got my 600 Newton pulling me back. That's equal to 0. So in this case, my driving force is just going to be 600 newtons. Okay, so you should be able to see that, but it's good to always write down your calculations. So my driving force is 600 newtons going forward. Okay, and the next thing that I'm going to do is I'm going to work out what is my constant velocity at which this thing is moving. And I am going to use, I don't really want to jump into my work done divided by time. I don't need to look at energy at the moment. So the formula that I'm going to use for my power is my driving force times my constant velocity in this case. And so we have 4,500 watts. I already know my driving force. And so I can calculate my V, which is just 45,000 divided by 600. And the constant velocity is 7.5 meters per second. Okay, so in this case, because it's going at a constant velocity, I can use my velocity is my change in distance over change in time. I only use this formula if I'm working with a constant velocity or if I'm working with an average velocity. If I'm not working with constant or average, I need to use SUBUT. So just keep that in mind. But because it's constant, I'm just going to use it. We already know our distance. Sorry, distance is 15, and our change in time is what we're wanting to calculate. So I just make my time the subject of the formula. I've got 15 divided by 7.5, which is 2 seconds. That is the answer to the first question. Okay, let's jump into part B. So the next part. The rope breaks after the crate has moved 15 meters. All right, so we've still got some friction. Now, all of a sudden, we don't have a pulling force because the rope is broken. Okay, so we no longer have, on our free body diagram, there's no driving force. The rope breaks after the crate has moved 15 meters. Find the time taken after the rope breaks for the crate to come to rest. Okay, so here we can see our sum of our forces is mass times acceleration. In this case, we expect the crate to be decelerating. The only force acting on this object now is my negative 600 newtons. The mass of my crate is 200 kgs, and so we can work out the acceleration. So in this case, I have negative 600 divided by 200, and that gives me negative 3 meter per second squared. Okay, so this crate is going to be slowing down. They said find the time taken. But once again, our question is asking for time. After after the rope breaks, for the crate to come to rest. So this is where our velocity is equal to 0. Okay, so the question is, what is actually happening here? The crate is being pulled initially, being pulled at a constant velocity. That constant velocity we already know is 7.5 meters per second. Okay, so it's been pulled at a constant velocity, and then all of a sudden it's no longer being pulled, so it's just slowing down. Okay, so when the rope breaks, let's go back to this picture. It's already gone 15 meters, but that's no longer part of the question. Now the rope breaks. At this point over here, at the very beginning, we know that the initial speed is 7.5 meters per second. We know that the final speed is going to be 0 meters per second. And we know that the acceleration is negative 3 meters per second squared. So we can use SUBUT to calculate this. There's a few things you could do. You could probably use energy as well. So all of the kinetic energy will be depleted with work done. But I think that's probably, yeah, I guess you could use either one. But let us go into SUBUT. So I've got my U, I've got my V, I've got my A, and I'm looking for T. So V is equal to U plus AT. Okay, if we look at our final velocity is 0, our initial velocity is 7.5. Acceleration is minus 3. And so our time is going to be 2.5 seconds. And that is the correct answer. All right. So each time it's just a free body diagram, and understanding questions like this where they say the rope breaks. Okay, what does that imply? That implies there's no longer a pulling force on this. Okay, next we have question 2. So a particle is projected vertically upwards from horizontal ground. Okay, so it's horizontal ground, the particle is projected upwards. The initial speed is 15 meters per second. Find the speed of P when it is 10 meters above the ground. Okay, so we don't know exactly where that is, so we'll just say 10 meters, and they want to know what is our final speed at that point. I always like to draw an arrow according to what I want to do in my Subat equation. So if I look at my Subat equation here, I've got u is 15. Because this is a projected particle, my acceleration is always gravity, and it's going opposite my arrow, so it's negative. My distance is 10 meters, and what am I looking for? I'm looking for my final velocity. So I've got, these are my 4 variables, so I'm going to use my equation v squared is u squared plus 2as. I can look at 15 squared plus 2 times minus 10 times 10. 2 times 10 times 10. Okay. And my final velocity, v squared is 25, so my v is going to be 5 meters per second. Obviously, it's positive because we're not going to be looking at the negative value right now. Okay, so when it is 10 meters above the ground, the speed is 5 meters per second, and that is the correct answer. All right, next question. At the same instant that P is projected, a second particle Q is dropped from a height of 18 meters above the ground in the same vertical line as P. Okay, so it's good to practice these types of questions. So P is going up, and then Q is coming down. And let's just say it's dropped from a building 18 meters above. Find the height above the ground at which the two particles collide. Okay, so when you've got something like this, Subat equations, and the particles are colliding, the note that you want to make is you want to be able to relate the two particles to each other. So I'm going to go with green once again for my Q particle. So here we know that our initial speed was 15. We know that our acceleration is minus 10. And then the two variables that we can generally relate to each other is time. Okay, so in this case, they are released at the same instant. So I'm just going to make time, and it's going to be the same for my P and for my Q. Okay, and then my distance. So there's different ways to do this. For the sake of this exercise, I'm just going to say that I'll call this S1, or let's say S of P. Okay, so it's moving S of P. You could label it X or something like that if you'd like to. Okay, now my other particle is dropping. It's dropped from a height of 18 meters above the ground. Okay, dropped implies, because it's not thrown down, so it's dropped. So my U is 0 meters per second. Now my acceleration is going to be 10 because I'm going down, so it's positive 10. My time, so when these two particles collide, it's going to have the same time in the formula. And then my displacement here, this is the trick. So if the green arrow, or my particle P, is moving a certain distance, my pink particle Q, is going to move a distance of 18 meters minus S of P. Okay, so the trick to these types of questions is to relate the two particles to each other. Normally you use displacement and time. Those are the two variables that are really going to help you relate them. Okay, so if I write up the formula, I'm going to use S is equal to UT plus a half AT squared. So in this case, I've got 18 minus S of P is a half times 10 times T squared. So if I just simplify this, I'm going to simplify it before I put it into a simultaneous equation. I might just make S of P subject of my formula. Okay, and then on this side, I have got S is equal to UT plus half AT squared. So I've got SP is 15t minus, well, 10, that's going to become 5t squared. Okay, so now I've got something where I can do a simultaneous equation because both of them are equal to SP. Make them equal to each other. This is quite nice. I can see that these 5t squares are going to cancel out. And that makes my answer quite easy. So 18 divided by 15 is going to give me 1.2 seconds. All right, now the question is that what they asked for? No. Find the height above the ground at which these two particles collide. Okay, so we figured out the time at which they collide, but can you see if I calculate my value for SP now, I'm going to get my answer. So I can plug that into either equation. I'm actually going to use this pink one, just because it seems easier. So 18 minus 1.2 squared, and that gives me 10.8 meters. So at a height of 10.8 meters, that's where they're going to collide. Right, so the tricks to these questions is relating your displacement and your time to each other. Watch out for, sometimes they say the particle is dropped 1 second later. Just watch out for questions like that as well. Can trick us a bit. Okay, next question. A particle moves in a straight line. This is always, they always need to give you this information if we're looking at kinematics. Okay, so the particles must be moving in a straight line. If it's not moving in a straight line, you would have to go to something like energy. So the particles are moving in a straight line from rest, okay, at a point 0. So my velocity at 0 is equal to 0. The acceleration of the particle at time t after leaving is given by this formula. Okay, so we can see that our acceleration is not constant. If we look at our different topics in mechanics, we're currently busy with kinematics. I like to split them into different categories. So you've got constant acceleration, and then you've got varying. So when your acceleration is changing all the time. Okay, if you've got constant acceleration, whenever you look at your time graphs, you can expect straight lines. So if my velocity, I've got acceleration is a straight line. Constant, this is my velocity, by the way, my velocity time. You expect straight lines on a velocity time graph, and you can also use Suvat. Okay, if your acceleration is varying all the time, then on your graph, you're probably going to have curved lines. Okay, your velocity time graph, and this is where you need to use, so in this time graph, you've got your area and you've got your gradient. Okay, so your gradient is your acceleration and your area gives you your distance. I'm just giving a broad overview here, it gets a little bit more complicated. If you have varying acceleration, then to get your area, you need to integrate to find the area under the graph. That also gives you distance or displacement, depending on what it looks like. And then your gradient at a point needs to be found by differentiation. Gradient is also acceleration. Okay, so that's just my little summary of kinematics. It gets more complicated, but that's the gist of it for now. So what you see is this is an acceleration question. It's varying acceleration, so we know we need to be doing integration and differentiation analysis. Okay. Find the speed of the particle when t is equal to 9. Okay, so what's the velocity when my time is 9? Okay, so we don't have a formula for velocity here. We've got a formula for acceleration. So the other part of this information that you need to know is you can move between displacement and integration. If you're moving down from displacement to velocity to acceleration, you need to differentiate. Okay? Because, for example, your acceleration is your change in velocity over change in time, or dv dt, so you differentiate. For velocity, it's your change in distance over change in time, or ds dt. So here you can see you need to differentiate. And then going back up, we know the reverse is integrating. Okay, so if you are unclear, this is very good theory just to take a note of. Okay, I've got lots of theory notes going on here. So we've got acceleration. So in order to find velocity, I need to go up my ladder, which means I need to integrate. I'm doing an indefinite integral. I'm just going to find the equation for velocity. And that is my integral 40 to the power of a half. And I'm going to integrate in terms of t. And that's going to give me, so I'm going up. Okay, so I keep my coefficient. I'm going up a power. And then I'm dividing by the new power. And I need to remember plus c. Okay, so if you're ever getting the equation, it's not a definite integral. You must remember plus c. Okay, so now I've got 8 over 3 c to the 3 over 2 plus c. Okay, and they gave me a point. That's why I wrote it down in the very beginning. It's when it's starts, it's at rest. So when I plug in, my t is 0, my velocity is also 0. And so what I end up calculating, my v of 0, probably good to show this. C is equal to 0, so this is equal to 0, so c is equal to 0. So my velocity time equation is 8 over 3 t to the 3 over 2. Okay, find the speed of the particle when the time is 9. So once you have a formula, then you can plug in your 9 and get your answer. So 8 over 3 and then 9 to the power of, then I just type into my calculator 9 to the power of 1.5. I find that is easier. 9 to the power. Okay. Okay, sorry. You do need to put into your calculator 8 over 3 times 9 to the power of 1.5. And that gives me an answer of 72 meters per second. And that is the correct answer. Okay, so just understanding what topic you're in, knowing that you need to differentiate and integrate. In this case, our C value ended up being 0, but you might need to calculate a C value that's not 0, so just watch out for that. Okay, that's the gist of it. If we go into the next question, it says find the time after leaving 0. So find the time, so we need to find a time. It's good to know what you're aiming for. After leaving the origin, at which the speed in meters per second and the distance traveled in meters are numerically equal. Okay, so speed does not equal a distance, but they're saying are numerically. So for example, 3 meters per second would be numerically equivalent to 3 meters. Okay, so don't worry about the units for now. They want us to know when those two things are equal, what's the time? Okay, so let's just figure this out. Find the time at which the speed and the distance are numerically equal. Okay, so we need a formula for velocity, which we already have. So that's 8 over 3 t to the half. Now we're going to get the formula for displacement as well. So let's maybe do that first. So my displacement, I've got to go up again. So I already have my velocity formula. Now I want my displacement formula, so I'm going to integrate again. It's an indefinite integral. So I need to calculate my C value. Okay, so here we're going up a power. Sorry, I should have just kept my coefficient. Go up a power and then divide by the new power plus C. Okay, so sometimes I like to just over exaggerate my fractions, otherwise I can get confused. So divided by 5/2. Okay, plus C. Okay, I just want to work this out. So if they're moving from point 0. So at my time is 0, my displacement is also going to be 0. So here I can see that my C value is also 0. Sorry, my C is equal to 0. So my displacement, 16/15 times 5/2. Okay, this is a very interesting question because now we are not looking at, okay, we are looking at where does the velocity equal the time, equal the displacement. Okay, so my velocity answer must equal to my displacement. Okay, let's see if we can solve this. This is a really random question, but it's good to keep our heads about us with random questions. Okay, the first thing that I see here is a lot of complicated powers. All right, so I would suggest knowing a bit of theory on how to solve these. What I'm going to do is I'm going to take my 8/3 to the other side. That becomes minus 8/3 t to the 1.5. I'm taking it to the other side, but then I'm just equating it to naught and I'm writing it on the other side. So just make sure that you are fine with what I did there. The reason that I did this is I find it the easiest way to solve these powers is now by factoring out. You factor out a t and to the lowest power. So I'm taking out t to the 1.5, and I'm generally left with just a single t. But I want to check now. Okay, so this is t to the power of 1. So when I multiply back in, you need to remember your exponent laws. When you multiply back in, you're going to end up with t, and then it's 1.5 plus 1. So you add your exponents when you're multiplying exponents. Okay, so we end up with t to the 5/2, and that is what we had here. So it doesn't always end up that there's one t left, but normally it does. So I just start with writing 1t, and then I see does it equal what I want it to equal. Okay, that's just my way of doing it. So here you've got two factors. There's your one factor, and here's your other factor, and these are equal to 0. So if your factors are equal to 0, you can say t to 3/2 equals 0, or my other factor is equal to 0. So in other words, t is equal to 0, or t is equal to, and then I'm going to take my 8/3 to the other side, and I'm going to divide it by 16/15, which becomes 5 over. Okay, now have I answered the question? They say find the time at which the two are numerically equivalent. And so we have found the time. Oh, which one of these is correct? Find the time after leaving the origin. So we are not going to calculate, we're not going to consider that one. We're only going to consider this one because they've already left now. Particles have already left. The particle has already left point O. Okay, so that is question 3 for you. I hope that's making sense. Let's keep going. Okay, according to this video, we're about 29 minutes in. So let's just keep going. All right. A toy railway locomotive has a mass of 0.8 kgs. Okay, so this is like a train engine, and it's towing a truck of that mass on a straight horizontal track. So before I draw, I just want to know, is it horizontal or is it inclined? In this case, it's horizontal. By the way, you don't need to, I do recommend you make a drawing. Sometimes it does, you don't want to take up your space, so you can just do a small drawing over here. This is my engine, and it is towing a truck. Okay, it doesn't matter what it looks like. this is 0.4 kgs and this is 0.8 kgs, and we're looking at poise here, so obviously it's not realistic. Okay, on a straight horizontal track at a constant speed. Okay, that means all the forces going forward is equal to all the forces going back. If I look at Newton, my acceleration is going to be equal to 0. Okay, there's a constant resistive force of 0.2 Newton on the locomotive. Okay, so this has a constant force of 0.2 Newton. There's no resistance force on the truck. Okay, so nothing is pulling the truck backwards. There is a light, rigid coupling connecting the locomotive and the truck. So this doesn't have a weight, but it is rigid. Okay, so it can take tension and compression. That's important to note. Okay, state the tension in the coupling. Okay, so they just say state, so you don't actually have to do any calculation. You can just write down the tension. What I want to quickly do for myself, because they said that, I actually don't want to do too much of a drawing. I just want to write down. If I look at my locomotive, it's not accelerating, so I know my driving force is going to be equal to my tension and my friction. Okay. Do we know the tension? Not yet, and we don't know the driving force either. Okay, so if I look at my truck, I'm just orientating myself here with this question. If I look at my truck, I've only got the tension pulling it forward. I've got no resistance forces pulling it backwards. Okay, so it looks like my truck might aid me in calculating this thing. Um, the sum of my forces is my mass times my acceleration. State the tension in the coupling. Okay, I feel like the tension needs to be 0. Do you know why I'm saying that? I'm saying that because there's no resistive forces on this truck, and the sum of my forces needs to equal 0. So my sum of my forces is mass times acceleration. The only force that I have here is my tension pulling it forwards. I don't have any friction, so if tension's the only thing and it's not accelerating, tension must be 0. Okay, this feels like a bit of a interesting question, but it makes sense. And I think the reason for that is there are no resistive forces, okay, and it's traveling at a constant velocity. So you can try to imagine that. If you think about going up and down an elevator, this is how connected particles work. If you're going up an elevator, when you accelerating, you can feel like gravity pulling you down. So the tension in the rope is quite strong. And then when it travels at a constant velocity, it's going to be, you don't really feel gravity that much. And then when it slows down, it almost feels like your stomach is floating a bit. So the tension is less. So the tension is changing according to acceleration and deceleration. It's not to say that the middle part always has 0. That depends on the frictional forces and stuff like that. But if you look in this case, there's no frictional force on the trailer, and so our tension in the rope is 0. And that does look like the correct answer. Okay, find the power produced by the locomotive's engine. Right, so power, when I hear that word, I know power is work done divided by time, and power is my driving force times my velocity. So in this case, I'm most likely going to be looking at my driving force times my velocity, because we're not looking at an energy question right now. Okay, so power is my driving force times my velocity. We have the velocity. They gave us 2 meters per second. We don't have the driving force. So here, what we're going to do is I'm just going to zoom into my little locomotive. I know that my sum of forces is mass times acceleration. I've got my tension pulling it back, my friction pulling me back, my driving force pulling me forwards, and it's all equal to 0. Okay, in this case, we already worked out that tension is 0, nothing else changed. We've got a frictional force of 0.2. So that basically means my driving force is 0.2 newtons. And then if we look at our power, we've got 0.2 times 2 meters per second, which is just 0.4 watts. Okay, so don't let this is now weird because it's so little, but remember we're working with the toy system. Okay, so that's what it looks like for now. That's what it looks like for now. Okay, next, the power produced by the locomotive's engine is now 1.2 watts. Okay, so it's a lot more. So we can expect this thing to now be accelerating or something like that. Find the magnitude of the tension in the coupling at the instant that the locomotive begins to accelerate. Okay, so at the instant, we need to remember this. At the instant, this keyword, my notes for this keyword is power. Power can jump. Okay, so in this case, it jumped from 0.4 to 1.2. It can jump quickly. Okay, velocity can't. Okay, so it can't just go from one velocity to the next. You need to go through all the different velocities. Okay, this is a general circumstance. Sometimes if something hits a wall, they'll say like the ball hit the wall and it lost energy. So there is a jump in velocity there. But in a general circumstance, if you're just changing the power, velocity can't jump. So we were working with 2 meters per second, and now we're still going to work with 2 meters per second at that instant. Okay, so we've got our power is driving force times velocity. And in this case, we've just got 1.2 in our driving force, and we're going to use the 2 meter per second. So our driving force is very small, 0.6 newtons. All right, so it is a bit weird working in such low values, but we need to remember it's a toy, so just keep going with that. Now they say find the magnitude of the tension in the coupling. Okay, so as soon as this thing starts to accelerate, it is going to change the tension. So if I look in my locomotive, I've got my driving force going forwards, and then I've got my frictional force and my tension pulling me back. So my sum of my forces is mass times acceleration. So minus tension minus friction plus my driving force is now going to equal my mass of my locomotive, so 0.8 times A. Right, tension is no longer 0 because this thing is going to be accelerating. I do know my friction is 0.2, and I know my driving force is 0.6. So I've got minus T. I don't know why I'm using a calculator right now. So this is 0.4. Okay, so if I just maybe make tension the subject of my formula, I've got tension is 0.4 minus 0.8 A. Okay, and then if I look at my truck has got my tension pulling it forward and there's no friction pulling it back. Okay, so in this case, we've got my sum of my forces is mass times acceleration. So tension is pulling it forward, and my mass of my truck is 0.4 times my acceleration. Okay, so because these are connected particles, it's got to be the same tension in the rope, so that's the same T, and it's a rigid bar, so we've also got the same acceleration going on here. So I can do a simultaneous equation. 0.4 minus 0.8a is 0.4a. So 1.2a is equal to 0.4. So my acceleration is going to be so 0.4 divided by 1.2 Acceleration is just a third, 1/3. Okay, and what did they ask for? Find the magnitude of the tension in the coupling the instant it starts to accelerate. Okay, so now we've got to go back to just find out tension. In this case, we're going to say 0.4 times 1/3. And my final answer is 2/15 newtons. And I'm going to leave that as a fraction because it's neater than decimals and rounding off. Um, and that looks exactly like what they're looking for. Okay, so very small tension, 2/15 newtons. Okay, jumping in, how many questions do we have? We've got 3 questions left. Okay, let's jump right into question 5. So this is an interesting thing. As soon as I see this, I think free body diagrams. So immediately in my head, I want to just label these degrees, draw that separately, and then ultimately I'm going to erase my platform. Okay, this is sort of what's going in my mind as soon as I see this question, but let's actually read it and see what's going on here. All right, so they say the diagram shows the block D of mass 100 kgs. Okay, this is interesting. What I do want to put here is my vertical force going down of 100,000 newtons. Okay, so the mass is 100 kgs and it's supported by 2 sloping struts. AD and BD. Okay, so a strut is going to be rigid. Okay, so it's like a pole keeping it up. Okay, each is attached at an angle of 45 to a fixed point A and B on a horizontal floor. Great. The block is also held in place by a vertical rope CD. Okay, so there's a rope hanging and there's 2 poles keeping it in place. Okay, the tension in rope CD is 500 newtons, so they've given us that. And the block is at rest in equilibrium. Find the magnitude of the force in each strut, AD and BD. Ooh, okay, so what is interesting here about a strut is going to end up being a compressive force. Okay, so it's like a pull keeping this weight up. So the forces on this thing actually look like that. Okay. So if I'm going to go, I'm just going to label it F1 and F2. I'm not using T1 and T2 because it's actually a compressive force. Okay, I think I'm going to redraw this particle. So if I draw my particle, I know that I've got 500 going vertically up. I've got the weight of this thing going vertically down. I've got a strut with my F1 force, and that's at 45 degrees. And I've got another strut, my F2, also at 45 degrees. Okay, so this is maybe a little bit tricky just to bend our heads around it because most of the questions that was asking for tensions. It's a little bit different. But as soon as I've got my free body diagram, it's the same. Sum of my forces in the x and the y are equal to 0 because it's in equilibrium. Okay, so if I look at the sum of my forces in my x direction, okay, so basically this thing has a component in the x direction. Let's just put that in there. And then this one over here also has a component in the x direction. And those are my only 2 forces in the x direction. Okay, so I'm going to say minus F2, and that can be sine or cos, by the way, that because 45 is 45. Let me just think the correct thing would have been to put cos. Okay, plus F1 cos 45 degrees, and that is equal to 0. Okay, so sine or cos 45 is the same as root 2 over 2. Okay, but we are going to need to be doing simultaneous equations here. The sum of my forces in the y must also equal to 0. Okay, and then here, if we just break this down into y components, so once again, my blue, I'm going to just use my blue and my green. So I've got a y component going up. Let's roll and put that one on that side. And then I've got my y component also going up. And I've got my 500 Newton pulling it up. And I've also got my 1000 pulling it down. Okay, so there's 4 things in the y direction. So we've got 500 going up minus 1000 going down. Okay, and then my 2's are also sine 45. Okay, so I've got, let's just take this to the other side. That's going to become 500. Once again, this is root 2 over 2 f1 plus root 2 over 2 f2. Okay, so I'm just going to see if I can make my life quite simple here. If I were to make root 2 over 2 f1 the subject of the formula, okay, basically we're going to end up with f1 is equal to f2. Okay, and now if I want to solve this one, I can say root 2 over 2 f1 plus root 2 over 2, and then I'm going to change this to an f1 so that I can actually solve. Okay, so this is quite cool. And does it make sense? Yes, I think it makes sense because this thing is quite symmetrical. Okay, so I should have known that. The answer is root 2 f1. Okay, so my f1 is equal to 500 divided by root 2, which is 354 Newton. Okay, that's 3 significant figures if I round it off. And so that means to find the magnitude of the force in each strut. And force in my second strut is also the same thing. Okay, you might want to label it the force of AB and the force of, the force of AD and the force of BD. And the force of, how we said BD. Okay, so just to make it clear. But if you did put your 1's and 2's on your diagram, you are more than welcome to use your 1's and 2's. Okay, now next question. A horizontal force of F is applied to the block in the direction parallel to AB. Okay, so now we're applying another force on this thing, parallel to AB. So I don't know exactly which direction it's going. Horizontal force of F. So now we need to label it F because that's what they give us. Okay. Find the value of F for which the magnitude of the force in strut AD is 0. Okay, so this is helpful to have a little bit of imagination. Okay, so if we are looking at this force, AD, it's going to be carrying a lot of weight. Okay, let's say there's no force pulling it horizontally. Okay. If we pull this a little bit to the one direction, it means the weight in this strut over here is going to increase. It's going to become heavier on that side. Okay, and in turn, it means it's going to become a little bit lighter on this side. If you pull it even more on this side, this is going to get even heavier, and this one is going to get even lighter. Okay, so I always like to just imagine even heavier, and eventually this thing is not going to be carrying any weight at all. It's going to just be as if it wasn't there. Okay, and that's basically what they want to come down to. So when they say calculate, find the value F, find the value of F for which the magnitude of the force in strut AD is 0. Okay, so basically we're going to remove AD from our picture. That's how to make it 0, is remove it from the picture. And we will still be having an F in here now. Okay, So this thing is still going to be in equilibrium. It's not moving anywhere, but the weight is now moved over so that everything is in BD. Okay, so the sum of my forces in the x direction. And now we've got, I'm just going to bring this down. Okay, sum of forces in the x direction, I've got my minus F2 cos 45 degrees, and then I've got my F moving it forwards. That should be equal to 0. So my F is going to be F2, so it should be root 2 over 2 F2. The sum of my forces in the y direction is also equal to 0. So now I've got my F2 sine 45 plus my 500 minus my 1000. And that's equal to 0. There's nothing else in the y direction. So we've got F2 is equal to 500. So F2, well, 500 and then divided by 2 over 2. And that's 707 newtons. And so my F becomes 707 times root 2 over 2. And that becomes, oh, my F is just 500 newtons. All right. And we have got, let's just take a look, and that is the correct answer. Okay, so the easiest thing that I find with this one is to just imagine what's happening so that you know that you understand the question properly. Okay, and then draw a free body diagram. So in this case, I'm removing that force because the force is there. Okay. All right, we on our second last question. Done 52 minutes. Let's see how fast we can go. Obviously, if I was doing an exam, it would be a bit quicker, but I still want to see if we can finish as fast as possible. Okay, so block B of mass 2 kgs. So as soon as you know it's 2 kgs, 2 kgs, or it's 20 Newton, directly down, lies on a rough incline. Okay, so we've got to add in friction. I don't know yet which direction this thing is going at. Rough incline sloping at 30 degrees. A light rope inclined at 20 degrees above the line of greatest slope is attached to B. The tension in the rope is T. There's a frictional force of F on B. Okay, so we can expect that. So if the frictional force is actually down, it means that this whole box is wanting to go up. Okay, otherwise it would be the other way around. Okay, the coefficient of friction between B and the plane is mu. All right, it is given that F is equal to 5 and the acceleration of B up the plane. So they've given us this is 5 Newton, and we know that the acceleration is 1.2 meters per second squared. Find the value of T. Okay, so a few things we need to know here. Every time we see an incline, we also need to add the weight component. Okay, so if you see an incline, add weight. If you see friction, add the frictional force. In this case, we're only looking in the direction of motion, so we're going to have to work out our T cos 20. Okay, we know that the sum of the forces is mass times acceleration. So if I look in my line of movement, I've got -5 minus my weight component, so that's 20 sine 30, and I've got my T cos 20 going up, so minus weight minus friction plus T cos 20, and that is my mass times the acceleration which they gave us. Okay, so just make sure you haven't left out anything when you're doing these questions. Okay, so I'm going to say 2 times 1.2 plus 5 plus 20 times sine 30. Okay, and the whole thing divided by cos 20 gives me 18.52 newtons. So if I were to go to 3 significant figures, I would just say 18.5 newtons. Right, that's my T. I guess the important thing is just not leaving out anything, looking in the direction of motion. All right, find the value of mu. Okay, so find the value of mu. So we know our frictional force. Frictional force is mass times acceleration. Frictional force is mu times r, our normal. Okay, so we know what our T value is now. Our frictional force they already gave us is 5. We don't know our mu. And now r. If we look at r is, we've got our r value coming up here. R is the resultant force of all the forces in the y direction. Okay, so we need to be careful. The reason we need to be careful is here we've got our weight component going down. So I'm going to include this going down. That's mg cos of theta. Okay, and then we also have our t is lifting it up a little bit. Okay, it's lifting it up this little bit over here. So that's t sine 20. Okay, so whenever you are solving for the normal force, whenever you're solving for a normal force, make sure it's in the y direction. Make sure you're looking at all the forces in the y direction. Okay, so we've got our minus mg cos theta plus, so that's our weight component, our t sine 20. And then plus our r is going to be equal to naught, okay? Because this thing is not going floating up off the plane or sinking into the plane. So the sum of the forces in the y direction is 0. Okay, our mass is 20. 20 cos 30 plus t sine 20. We know that our t is 18.5. So our r value is going to be 20 times cos 30 minus 18.5 times sine 20. And that is giving me 10.99. So my R value is basically 11 newtons. Okay, I think if I were to keep all my significant figures all the time, I would end up with an exact value. And that is making my mu 5 over 11, which is 0.455 if we round off. Okay, and that is also the correct answer. So it's very exciting. Okay, so the trick for that one is don't just take the opposite of weight, the weight component. You need to remember the t component in there as well. Okay. Now, it is given instead. Okay, if you ever see that, it is given instead. So just go and look at how they wrote up the question. They say for part A, so all of this is still true. Okay, the introductory paragraph is still true, but the information for A is now no longer valid. Okay, so F is not 5 and the acceleration is not 1.2, but the top stuff is still the same. Okay, it is instead given that mu is 0.8 and t is equal to 15. Determine whether B will move up the plane. Okay, so we just need to, I'm just going to redraw this thing. I've got my, okay, so friction, depending on if it's going to move up or down, friction is going to act up or down. Okay, so in this case, they have given us T is 15. Okay, we've still got our mass of 20. And now we don't know, so I'm just going to say this one is mg sine 30. We don't know is friction or acting up or down. Okay, so what I want to do is I want to see what does my tension force look like going up and what does my weight look like going down. A weight component acting down. So mg sine theta, how much weight is that? So that's 20 sine 30. So weight going down is 20 times sine 30. I'm just giving this a 10 newtons, okay, and then my T going up is 15 times cos of 20 is 14. 15 times cos 20 is 14. Okay, so it looks like my component pulling up is more than my weight component pulling down. So it's going to want to go up, but we still have to work out if it does go up or not. And that's where we've got to look at friction. So it wants to go up. Okay, so now our frictional force is included. The sum of our forces is mass times acceleration. So we've got our weight component going down. I'm just going to say minus 10. We've also got our friction going down, and we've got our 14 going up. So this is 14.095. So I'll just say 14.1. And that is equal to our mass times our acceleration. Okay, minus 10 is the same as mu times r. Okay, we know our mu, which is 0.8. So do we know our r value? Okay, here we need to go and look again at our r value because what changed? Our value for t changed. Okay, so if we go and do another sum on the side, our sum of our forces in the y direction should be equal to 0. So we've got our weight components going down plus our tension from sine 20 going up plus our r is equal to 0. Now we know it's 15 sine 20. So we can calculate our r value. So our r is 20 times cos 30. So can you see how every single time a y value changes? Okay, so that's 12.19 Newton. Let's just say 12.19. Okay, and so here, let's just work out our acceleration. So minus 10 minus 4.8 plus 14.1. Okay, and what we have here is that it looks like we're getting a negative acceleration, which means that this thing is probably not going to go up the hill. So I just want to work out separately, what is our frictional force? So our frictional force is minus 0.8 times 12.19. Okay, so I'm not going to actually add a direction for now. I'm just going to say 12.19 times 0.8. Okay, so our frictional force is basically 9.752. So if it wanted to go up, this is the frictional force. This is your maximum frictional force, okay? So if I look at my block, we already worked out that there's a 10 Newton going down because of weight. And now this thing can also have a frictional force of a maximum of 9.752 going up. And then we've got 14.1 pulling it up. So can you see that this block is not going to go up the hill? The frictional force can resist, it's going to resist up to 14 Newton. So the total here going down, oh, this is obviously going to be 19.752. That's how much it can resist. If friction is working at its absolute maximum, between the weight component and the friction, it can resist 19.752, and we've only got 14.1 pulling up, so therefore the box is not going to move up. Okay, this is a really interesting question. I hope that that made sense to you. We are so close to finishing, so we've got one last question. It's question 7. As soon as I see a curve here, all I can think of is energy, because you can't use Suvat or kinematics or anything if you have a curved line. It must be in a straight line. Okay, so I'm thinking energy. There's a part A, B, and C. Let's see what we can do with this. Okay, so A, B, C, E. I don't know where D is, but anyway. The diagram shows a smooth track which lies on a vertical plane. Okay, so it's lying upwards, so it could be like skiing and jumping, something like that. Section AB is a quarter circle, right? With a radius 1.8 and the center O. The section BC is a horizontal straight line with the length of 7 meters, and OB is perpendicular, okay, to BC. Section CFE is a straight line inclined at theta degrees. Okay, so everything that we see on the diagram is basically what they just described. A particle P of mass 0.5, so now I'm going to add my P. The mass of this thing is 0.5 kgs, is released from rest at A. So it starts off with 0 meters per second or no kinetic energy. In an energy question, that's what it implies. Particle P collides with particle Q of mass 0.1 kg. So there's another particle here, Q. Mass is 0.1, and it lies at rest at point B. Wonderful. Immediately after the collision, the speed of P, okay, speed means they don't give you the direction. Is it going forwards or backwards? You just take note of that. Speed of P is 4 in the direction of BC. Okay, so they collide, and then P is going at 4 meters per second, and they do give the direction. You should assume that P is moving horizontally when it collides with Q. Okay, just to keep linear momentum. Show that the speed of Q immediately after the collision is 10. All right, so this is now energy and momentum all in one big question. So in order to do momentum, we need to work out at what speed does P arrive at this particle. Okay, this is all hypothetical. Let's just take note. It is a smooth track, so there's no friction on this thing. Okay, so because it's curved, I need to use energy. Okay, don't go into anything other than energy. All right. In this case, the particle is going to have potential energy. So I like to have my little checklist. Potential energy, kinetic energy, work done by frictional force, or work done by driving force. Okay, so we don't have any work done. All of our potential energy needs to be dissipated into kinetic energy. Okay, so my EP goes to EK, and EK is going to give me the speed. Okay, so this is mgh is a half mv squared. Just out of interest, you can cancel out the m's. Okay, so 10 times my height, 1.8, is a half v squared. So my v, this is now the velocity at which this thing is going to arrive at point P. So I'm getting v is 6 meters per second. Okay, so it's good to just practice different types of questions and know how to ask them. Okay, the particle P is arriving at B with 6 meters per second. Now we can just jump into momentum. So my mass of P times my velocity of P, so mass of Q times my velocity of Q is going to be my mass, sorry, this is my initial velocity, P, P, P. Okay, so I've got a mass of 0.5, and that's going at 6 meters per second. This is initially at rest, and then after the collision, it's moving at 4 meters per second. My particle B has a mass of 0.1, and we don't know, not particle B, particle Q. Okay, so we want to work out, that's the only unknown. Watch out for signs in momentum. In this case, everything is moving to the right, so it's all positive. And my velocity at Q is 10 meters per second. Okay, so, and they said show that, right. As soon as I've shown that something and I get it right, I make a big, like, tick, tick, tick. I don't need to go back and check this because I already know the answers, right? They told me to prove it and I did prove it. Okay, unless you're getting there by chance, but if you're confident, well, if you've got a good idea that you know what you're doing, you should be confident that you've got the right answer. Yeah? Okay, let's keep going. When Q reaches C, when Q reaches C, all right, so now P is in front of Q and it's moving, and Q is moving after it and it reaches C. So you just have to know that these are hypothetical situations, okay? So Q is finally going to get to point C. P is still traveling and going probably up and down, okay? 4 meters per second, and this is 7 meters. Okay, so when Q reaches C, it collides with R, mass 0.4. Oh, hold on, let's just see. So, oh, okay, wait. Particle P is behind particle Q. Oh my goodness. Okay, hold on, I got the wrong thing here. So Q is going forwards at 10 meters per second. Okay, and P is coming after it at 4 meters per second. So you just got to keep these hypothetical situations in your head. Q is going forwards at 10 meters per second, and it bumps into R. Okay, the two particles coalesce. Combined particle comes instantaneously to rest at F. Okay, F is somewhere on the slope. And this is where velocity is equal to 0. Okay? You should assume that there's no instantaneous speed when they coalesce at C, nor when it passes through C again as it returns down the slope. Okay, so as it's going over that bump, no speed is changing. Very hypothetical. It is given that the distance, CF, by the way, here they're giving information, and I imagine they're going to change that information here. Okay, but I'm not sure, but that's normally how they do questions. Okay, given that the distance CF is 0.4 meters, find the value of theta. All right, cool. Don't you just love this? Okay, such interesting questions. All right, so I don't know. I like to do these questions by drawing, okay, and just thinking about every single thing that I'm doing. Okay, so I just want to double check, is this a smooth track? So everything is smooth. So A is not, Q is not slowing down as it goes from B to C. Okay, so in other words, particle Q let's just make sure the diagram. Okay, it is a smooth track. There's not a trick here. Okay, so this means that Q is going to hit this particle with 10 meters per second. Okay, that is what it is. So I'm just gonna write down MQ UQ plus MR QR is equal to, now they're gonna coalesce. MQ plus MR times my velocity. Okay, we might need to set this up and then come back to it later if we don't have enough to solve it. Okay, so my mass of Q is 0.1 times 10 plus my mass of R is 0.4 times 0. Sorry, so that should have been 0. And here, basically, our 0.1 plus our 0.4 is 5. And we need to figure out at what velocity they are now going to go up the hill. Okay? Calculator. All right, so it looks like we've got enough information to find this velocity. So 0.1 times 10 plus 0.4 times 0. Okay, I should put that in my calculator. Okay, 0.1 times 10 divided by 0.5. So I'm getting that these things start going up with a velocity of 2 meters per second. Yeah. So what is that? That's the velocity right over here as they start to climb this hill. They're going to be going up at 2 meters per second. Okay, this is a straight line, so you may use Suvat. So if I were to use Suvat, let's just see if I want to do that. If I were to use Suvat, my U is 2 meters per second, and it's not changing, even though it's going up the hill. My V is 0 meters per second, and then they give me my distance of 0.4 meters, not per second, just meters. Okay, and we in this case would want to work out our acceleration. Okay, time has not really got much to do with this question. Okay, so V squared is U squared plus 2AS. So my acceleration is going to be negative, and that's expected. It's decelerating. So 4, and my acceleration is -5. Okay, that's expected. So it's particles just sort of being hit up a hill. Obviously, they're going to slow down, otherwise they're not going to come to 0. Okay, so if we now think of our particle, we've got 0.1 plus 0.4, so that's 0.5 mass. The only thing acting on it is mg sine theta. It's the only force going downwards. So sum of my force is mass times acceleration. So minus 5 sine theta is equal to 0.5 times minus 5. Here we've got a half, and my inverse sine theta is therefore going to be 30 degrees. Cool question. Okay, what I really like about this question is everything is smooth. As soon as you added in friction, it would, cause a lot more calculations to need to happen. Okay, last question. I see we've gone over our technical exam time. Obviously, I'm explaining a lot more in between, so we need to work a lot faster, just to have time to check as well. Okay, so find the distance from B at which P collides with the combined particles. Okay, find the distance from B. All right, okay, so what's happening here? What's happening here now is that these particles are going up and down the hill, up, down, and P is coming along at 4 meters per second, and at some point they're going to collide. And they want to know, find the distance from B at which the particles, at which find the distance from B. Okay, so they want distance from B at P, at which P collides with combined particles. Okay, so I think this is once again just a drawing that needs to happen. Okay, so P, when P collided with Q, Q is going at 10 meters per second, and P is going at 4 meters per second. Okay. This is P, this is Q. So I'm just going to go each step of the way, and I'm going to take like snapshots. When Q is there, where is P? When Q is there, where is P? When Q is there, where is P? Okay. Right, so Q is moving along for 7 meters. So let's just see its constant velocity. Okay, so you can use velocity is change in distance with change in time. So this is going at 10 meters per second for 7 meters. How long did it take? 7 divided by 10 is, I don't know why. Okay, 0.7 seconds. Okay, so now this snapshot, Q is now already at the end over here. And my question is, where is P? So velocity is change in distance over change in time. So this thing, P is moving at 4. We don't know the distance in this case, but we know the time. So displacement of P is 4 times 0.7. So P has traveled 2.8 meters. Okay, so now if I take a look at my next snapshot, well, at this snapshot that I just calculated. So P is at the point of collision with R, and Q is at the point of collision with R, and P is now 7 minus 2.8. P is now 4.2 meters away. Okay, so it's moved a little bit forward. All right. Now, Q and R are going up the hill. So let's maybe figure out where are they? Well, how long does it take them to get up the hill and where is P at that point? Okay. Yeah, I don't know. I don't know if there's an easier way to do this. Let's just keep going. Okay. So in this case, we can't use change of velocity. Well, velocity is distance over time because now we've got not a constant velocity, it's changing velocity. Okay, so U is equal to 2, V is equal to 0, S we already worked out as, well, it's 0.4. What's our time that this is going to take? Okay, my Subat equations. I need my Subat equations. Let me just quickly. So you should have an MF19 next to you when you are doing these questions. I don't have mine here, and I normally know all my formulas, except now for this one. Okay, so S is a half U plus VT. Okay, so 0.4 is a half 2 plus 0, and how much time did that take? Okay, so 0.4 times 2 divided by 2. Okay, so it also took 0.4 seconds going up. Okay, 0.4 seconds going up. Right, so now they are over here. The particles are over here. And where is P? So P moved for another 0.4 seconds. So P, change in S, change in time, it's still going at 4 meters per second. Okay, so 4 times 0.4 is 1.6 seconds. No, 1.6 meters. Okay, so 4.2 minus 1.6 is now 2.6. So P has come closer. And at the bottom of this hill here, it is now 2.6 meters away. the bottom of the hill. Okay, now R and Q are coming down again. And basically, they're going to hit this point. It's going to take the same amount of time. It's the same distance. They're starting now from 0, and they're probably going to go to 2. So that's going to be another 0.4 seconds, and P is going to move another 1.6. So minus 1.6 is now P is 1 meter away. These guys come over here. Well, these ones come down, and P is now 1 meter away. Okay, that's at least comforting that P is not going up the hill as well. Okay, so now Q and R are at the bottom of the hill, and P is now 1 meter away. So can you see how each time I'm just checking where P is? There might be a easier way to do this. I haven't thought about it. It's the first time I'm seeing the paper, so I'm just kind of going for it. What we know now is it's a smooth track, and QR are now on the horizontal track again. So they're going to be traveling at a constant speed towards P, and P is still traveling at a constant speed towards it. Okay, so I'm going to use V is change in distance over change in time. P is moving at 4 meters per second, and I'm going to say P moves X meters. Okay? You'll see now why. It's good to relate these things. Okay? And we're just going to use time as T. And then QR, V is change in distance over change in time. So they're now moving at 2 meters per second, and they need to move 1 minus X in the same amount of time. Okay, so I've got 2T is 1 minus X. So X is 1 minus 2T. And then on this side, I've got 4T is equal to X. So if I do a simultaneous equation now, I don't know why I'm working out the time. It would actually be more helpful to work out X. So let's just say 2T 1 minus X, and 2T half X. So now half X is equal to 1 minus X. Okay, so there's different ways to do this. So 1.5 x's is equal to 1, so x is equal to 2 over 3. And that's where they're going to collide. Okay, so now let's just work out what is that total distance. So P, I think what I'm going to do is I'm just going to say 7 minus, no, x is 2 over 3, which means the leftover bit is 1 over 3. So minus a third, which is going to give me 6 and 2/3. That's how much P had to travel before it collided with other particles. Okay, let me know if you have a quicker way to do this. I really find it helps just to keep track of every time point. Where is what particle when? And remember, you can use, because it's a smooth plane, using constant hypothetical velocities. It's not, you won't really see this in real life. If it was rough, you would need to be calculating your acceleration each time and using SUBIT, not constant velocity. Okay, but that does bring us to the end of this paper. I hope that some of these tips are helpful, and all the best for your upcoming mechanics exam. I really hope it goes well. Okay, cheers.